Okay, everyone, welcome back. Our second speaker is Professor Yuan from University of Hong Kong. His research interests include numerical optimization, fast solvers for optimization problems arising in data science, optimal control, and scientific computing. He has done a lot of excellent research work on these topics. The title of his talk is An Operator Learning Approach to Non-Smooth Optimal Control of Nonlinear PDEs. Let's welcome Professor Yuan.
Thank you for the invitation, and I'm happy to come here again. I was here last year, and thank you for coming to my talk as well. So this is a work with some of my former students, PhD students, and the current students. It's something about how to apply operator learning, which is now quite popular in the machine learning, deep learning area, to the optimal control of some nonlinear PDE. So basically, this is a very, very difficult problem. So we don't have any theory result. We just focus on the numerical, application by combining the ideas come from the traditional optimization and some very modern deep learning techniques. So we don't focus on prove the error, prove the analysis, or some convergence rate. We cannot do anything about this theoretical stuff. So simply because of the complexity of the problem. So let me give you a very quick background and motivation review. So we can consider such a very general non-smooth optimal control problem. This is a nonlinear PDE constraints. So we have this is optimization problem, but the constraint is PDE, and the PDE is nonlinear. And we have some control variable. We want to control something. For example, we want to control the source of heat, and then we can control the temperature of the room. So we have to describe how the heat is transit from the source to other places. So we need the equation to simulate the physics, right? And then we control the temperature. So basically we can see in this model, S is a nonlinear. S is nonlinear. Any question? So basically, this means, okay, U is the variable we want to control, and the Y is the given state, this equation, and we want to, satisfy S and U should be satisfied with some nonlinear equations. So we want to, and the theta U basically is a non-smooth regularization term. Sometimes we need to regularize the data. For example, the most popularized L1 norm, for example, we need, for example, I just give you the example about how the heat transfer from the room, and we don't think we need too many resources for the heat, right? So we only need several. Like in this big room, we only have two. For air conditioning, we only have one air conditioner, for example, like this. So U, the number of U, so the sparsity of U is very reasonable to be assumed for this model. So so this is basically a very, very general model. It's non-smooth simply because theta is non-smooth. It's nonlinear simply because the function, the constant S, the PD is nonlinear. So this could be very, very general. So actually, a lot of real applications can be captured by this model. So just focus on this very genetic model. I'm going to give you some very general framework to see how to solve it. Just to list a very few applications, you can see these applications from Laurent Grovinsky. I learned this from Laurent many years ago. Leon's and many of their family students. They have been working on this for many years. So you see, just last talk, Professor Wang also mentioned some problems in the climate change forecasting and some ocean, the typhoon prediction. These kind of things, they are basically the PDEs, and sometimes we want to predict these PDEs. But there are many, many such applications. So mathematically speaking, there are some challenges, and there are some big challenges. But from optimization point of view, this first of all, this is non-smooth because of theta is non-smooth. So otherwise, you can just substitute y equals u into the object function, and then it's smooth function, right? You can use whatever you like CG. But now theta is non-smooth. So and then basically the gradient descent method, conjugate gradient, Poisson-Newton method, all these methods cannot be used directly, simply because we don't have the gradient, this non-smooth term. And as I said, because the function, the differential equation S is nonlinear, so it's equivalent speaking, there's some non-convexity. So the problem is non-convex as well. So traditional algorithms based on, for example, Feynman elements. We like Feynman elements method for many years. But whenever you use the finite elements, you are given. I mean, eventually you have to solve some very huge scale linear systems after discretization. So that's something you cannot avoid. And especially if you want to solve the system linear equations, even bigger problem is that for the nonlinear case S, the coefficient matrices in these linear systems actually are changing all the time. So you cannot do the prefactorize the matrix and keep that there for all the time. This is for linear case, you can do that. Because for linear case, you can just keep the matrix, do the factorization once, and you use that all the time. But for the nonlinear case, you have to do the factorization iteration by iteration. Right? That's a lot of steps to do. So there are, of course, there are many algorithms that you can consider in the literature. Like first of all, I think the most influential one is the semi-smooth Newton. And also we have actually there's many groups in the world, especially in Europe, that are working on the semi-smooth for the PDE or optimal control. And then, of course, from optimization point of view, some people like the sequentially quadratic programming method, SQP, and also some people extend the interior point method to this kind of nonlinear case. And you might know already, okay, actually interior point is the most famous algorithms for linear programming in the 1980s, 1990s. That's the standard algorithm. But still, some people consider linear interior points. But I'm not going to introduce any of them today. So maybe a little bit about SSN. So SSN method in one word is just to brute forcefully solve the problem by the semi-smooth Newton directions. So I can give you the formula. Actually, it's not difficult to give the formula about the SSN. But the problem is the implementation is very, very costly. So you have to, first of all, you say, I skip details, then you say eventually you have to solve this kind of projection equation. And the prox means like the proximum operator. If you don't know what is proximum means, basically, this is talking about projection, for example. Okay? And then S prime denotes the fractal derivative of S. And S prime star denotes the adjoint operator. So the SSN iteration basically means you have to solve each step. You have to solve this system equation, and the N, the matrix, the general gradient MK comes from the subdifferential. Okay, it's kind of it's not 100% non-smooth. We have some properties are wrong, so I'm not going to in detail. But in any case, actually, this partial phi defines the generalized differential, and the MK is one of them. So you have to know how to pick up MK so that you can solve the system equation. Now, how to pick up MK is a problem because partial phi could be very large. It's not a gradient. It's not differentiable, so it's not a gradient. So it's subgradient, and then subgradient could be huge. The set, and if you choose the different elements from the set, then you give different result. So this is it's very technical to consider how to choose MK. And that's also for this kind of things, it actually gives us a lot of troubles to choose MK. Anyway, so for each iteration, of course, you can apply the CG, for example, basically to solve the system. And for each CG, if we come back to the optimal control problem of PDE, for each CG iteration, you have to solve 2 PDEs. Simply for one single iteration, you solve 2 PDEs. And each PDE, as I said, is a huge linear system because of the discretization. So you have to solve a huge system linear equations. And I'm not saying it's easy or not, but you have to solve a huge system linear equations. And then, because as I highlight many times, S is nonlinear, so the corresponding matrices actually are different. It's not linear case. So you cannot do the prefactorize. So you cannot prefactorize matrix and you keep that as a constant, and each time you call this factorization. You cannot do that. That's why for nonlinear case, actually the computation cost is much, much higher. Deep learning, finally, so everybody now is talking about deep learning for different areas. So you see, we have seen a lot of deep learning methods for PDE in the past 10 years, I guess. So I can try to summarize a little bit. Okay, it's not the emphasis of today of my talk, but one deep learning method is what we call the solution learning method. We try to learn the solution. Okay, so we approximate the solution of a single PDE by deep neural networks, for example, DNNs. Okay, then we retrain the neural networks for a different PDE. So we try to learn the solution of the PDE. Okay, and of course, we have many, representative ways. In particular, the pins is very, very popular now. And of course, many people have different opinions of this. Not everybody likes this method. And of course, there's some, disadvantages about this. You use the pins. And then we have another way is called the operator learning. Operator learning means basically we learn the operator instead of the solution. The PDE is given by an operator in the left-hand side, in the right-hand side in the initial conditions, right? Kind of this boundary conditions. And then the operator learning means, okay, we are approximate solution operator of a family of parameterized PDE. Parameterized mean PDEs means we have the same operator but different parameters, different boundary conditions, different right-hand side, okay? And then after you learn this operator, then each time actually you just only one forward pass of the trained neural network for each PDE parameters is required. So we don't need to retrain the model. After we finish the training, just keep this, and that basically means the operator is known. So you give me the some other parameters, I give you the solution very quickly. We don't solve any PDE, okay, after training. So that's the operator learning method. This is some techniques I'm going to use today. And we have different ways to do operator learning. This is for PDE, deep learning for PDE. And of course, we have some extensions in the literature from the PDE to optimal control of PDE, okay, control of PDE. And so basically, most of the algorithms, as far as we know, are focused on the smooth case. The smooth case means we don't have the theta 1, we don't have the non-smooth functions in the objective. So everything is smooth. So we have people extend pins, people expand operator learning. And as I said, all of these algorithms cannot be extended to the non-smooth case straightforwardly. The case is the reason is because the non-smooth term, actually, if you want to use the pins, for example, to do this, then the non-smooth term is part of the loss function. Okay, so when you train these neural networks, then you have some troubles in the auto differentiation because of the non-smooth term. So you cannot do the auto differentiation for that. That's the main reason. When we have the non-smooth term, then the deep learning method cannot be used directly. So how can we do that? So for the non-smooth optimal control problem, I have been done this, since 2 or 3 years ago. So with my students and collaborators, we work on that. First of all, we use an idea from optimization to take apart the smooth and non-smooth components of the function. We use ADMM. So if you don't know ADMM, it's okay. This is just some method, some algorithm that can separate the functions as 2 parts. So we use ADMM. So one of the subproblems take care of the non-smooth part. The other one take all the others, and then all the others can be used by pins, for example. This is this tool. Or another one is quite it's quite different from the topics. But anyway, we use the pins idea to do the interface optimal control problem. So this is also Lai's professor in Taiwan, and all the others are my students or my former students before. All right. So anyway, when you do the deep learning approach, actually all these approaches I just listed in the slide needs to retrain the neural network for each subproblem. Meaning, at each iteration, you have to train the neural network once. Okay, that means a lot of work, of course. Okay. So let me give you examples. For example, we use ADMM for the optimal control of nonlinear PDE. Now we can do that very easily. Just follow the work of ADMM. In case you don't have no idea, let me give you a little bit more details. So we just introduce an auxiliary variable z. So we want to separate z, separate the non-smooth term. This is non-smooth term, right? All the others are the smooth case. So we just separate the z, separate the non-smooth and the smooth. So we represent z as the non-smooth case. And u, of course, we introduce a new constants. We force u must be equal to z. And we get this new model and one more variable. Then we do the ADMM. This is standard. Everything is standard. Okay. Grobinski is the people inventing ADMM. Okay. I'm one of the main followers. Anyway, so you see, we can do that. We can do the ADM. Very simple. Just if you happen to know augmented Lagrangian, this is a speeding version of augmented Lagrangian. Anyway, so we end up with these iterations. Okay, this is one of the iterations. Like we have to solve u, z, and lambda, 3 subproblems. And u is a smooth optimal control problem because theta z is absorbed in the second problem. The first subproblem has nothing to do with the non-smooth term. Everything is smooth. You can substitute y equal SU into the objective function, and everything becomes smooth. Now, no non-smooth term. And the only non-smooth term is in the second subproblem. And then the last step, of course, is trivial. Then everything becomes solvable, right? So we just apply the, the smooth case, the smooth deep learning method for the subproblem, for the first subproblem. This actually is just a very simple extension of our previous work. I didn't write any paper about this, but it's very easy to do this, thinking about this. Anyway, so this is an application of ADMM, but the problem is actually the use subproblem. You have to do, for example, you have to define elements, or you have to do optimization, whatever you like. And it's, again, it's a huge scale linear systems, cannot be prefactorized. And you can also apply pins. You can apply pins to do the subproblem. No problems to do that, but the problem is that you have to retrain the neural network, because whenever you change the different zik and the lambda k, all the constants actually give you different loss function in the frame of pins. So whenever you get a new zeta k, lambda k, which are different from iteration by iteration, and then you have to do the retraining. This is, this is the cost if you want to apply the pins directly. Okay? So applying the operator learning for non-smooth optimal control is the same. So this is our main motivation. So pins or operator learning for PD cannot be applied directly. So this is our motivation. We use a little bit of optimization. I start my career from optimization. I've been doing optimization for many, many years. So trust me, I know something about optimization. And then optimization, of course, is very important now. It's even more important in the future. But the problem is that not too many people in optimization care about other problems, from optimization areas. Okay, and so my motivation is, okay, we try to apply some very simple idea from the fundamental optimization algorithms to this problem, and if it gets, we can gain something. Let me show you. So we decoupled again the non-smooth term and the nonlinear PDE constraints, and then our target is actually the subproblems only involve evaluating solution operators of the PDEs with different parameters. Okay, the same operator but with different parameters, which can be handled by operator learning without retraining neural networks. This is our main message. We don't want to retrain neural network step by step. We just want to train the operator, just want to learn the operator and keep the operator there forever. So for each subproblem, we use the trained operator and just give different parameters, and then we get the solution immediately because the operator is supposed to be known already by the learning. That's our idea. So we do not require retraining. That's the main message. Okay, with different parameters, which is important for applications. Even, if you still remember the model in the very first slide, actually that model represents some applications, many applications. And for each of these applications, actually the parameters which define the model, the parameters define the model actually are changing if you try to apply this to real application problems. Okay, so that means if you want to solve, Professor Wang just mentioned, you need to keep, some data for months and years, and then for each time window, time segment, actually you have to keep solving the same model with different parameters. And then I don't think, we hope to solve the model from scratch each time. So that means for each such applications, actually we have to, keep solving the same model but with different parameters all the time. Okay, so we should, define, we should, design some algorithms which are not sensitive, so sensitive to the, to the constants. We hope actually we can have an algorithm that when you give different constants, I can give the solution very immediately. I'm not going to, solve that from scratch. You have to wait for another 10 days to get the solution. You know what I mean? So we try to learn the operator. We try to, by the training data, by the historical data, we try to, keep the information of the operator in our machine. And each time when you just change the model by the parameters, I can give the solution very, 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 very quickly. I'm not doing that, time by time or all the time from scratch. That's the main message. Anyway, so the solution or the answer to my questions, I can use the so-called parameter dual optimization algorithm to do that first. This is my first step. Okay. So you see, for doing that, we have to know something about the so-called set point problem. Whenever we have some, linear programming background or operational research background, you know what I'm talking about. So this is already a mathematical problem. So we want to minimize and maximize two variables together simultaneously. But these two variables are coupled by a cross interval. That's, for example, if you write the dual problem for linear program, you get this, right? So we have two variables to be minimized and maximized respectively, but these two variables are coupled by a coupling term. Usually, in the finite dimension space, this is the matrix. Okay, X transpose Y, U transpose P. That's this kind of things. Okay, so we want to do this, and T is linear. A G and the Y are convex, proper, lower, semi-continuous to make the problem well defined. So there's a very, very standard or classical algorithm we call the Chambon and the Park algorithm, which was proposed 14 years ago. Now that's one of the most popular algorithms in optimization. There are two algorithms which are now the most popular one. One of them is Chambon and the Park. The other one is ADMM. I mentioned both of them already in this talk. Okay. So anyway, this is one of the most popular ones. The idea is extremely simple. We just consider the primary variable and the dual variable separately. And the solution can be expressed by the proximity operator. Okay? The proximity operator, I can try to write them on the board just in case you have no idea about this. So the proximity operator is defined by, for example, we are going to minimize fx, right? And then sometimes we need to regularize this as below, x minus x squared. So if f is convex, then this is strongly convex. And the solution is unique, it's given, it's guaranteed by uniqueness, right? So we do the argument. We can do this instead of the original problem. So we can define the proximity, okay, of f as maybe alpha, okay, parameter rho. It's defined, we can define this as the argument, okay? We do the argument, fx plus. Okay, we can do this. This is the proximity operator. So we can, mathematically speaking, so we can do that. So the Chambon and the Park is okay. We separate the prime and dual variable, and then we do the minimization separately. And there's a parameter rho. This is what we call the extrapolation parameter in mathematics. Okay, it can be some number between 0 and 1. And this is the very, very famous one. And the algorithm, and it's very popular in image processing, for example, 10 years ago, 20 years ago. And we proved the convergence for the only case that the convergence can be proved is when rho equal 1. That's proved by me and my co-author, okay, 1 year after, several months after the work. That's the only case that the convergence is known at this moment, okay? And when rho is equal to 0, actually there's another method which is called the prime dual hybrid gradient, which was invented by Tony Chen and his former students in UCLA. That's 2008, I guess, several years before this one. So this is an application of the very famous error-observer method in PD, OD. Okay. In general, we gave a counter example. The PDHG is not convergent in general. So forget about the PDHG. Just focus on the case when rho equal 1. So that's okay. I give you a summary. If you are interested in this, you can read some of my papers. I give you the complete graph to see under which condition about the convexity of the function, and then we can have some different step size. But that's very detailed about the optimization. Okay. If you don't like, we can skip it. If you like it, we can take a look of this. In general, we see actually when rho equal 1 is convergent, it's proved by us. And if rho equal 0, it's not convergent. It's given. Counter example is given by us. And then if you have some strong convexity assumptions, sometimes the convergence can be guaranteed. And the step size can be slightly better, but I'm not going to detail unless you are interested in optimization. Anyway, so in this talk we're going to use this. So we try to reformulate the problem as prime and dual case, and then we can use the Chambon and the Park and the algorithms. So we just use that, and then this is the scheme. The 2 comes from the rho equal 1, the extrapolation. As I mentioned, this is the only thing we can get the convergence. Anyway, so we can do that. We can do that just by applying applying the prime and dual. So the scheme is very simple. And so let me give you more details about this. Of course, if you want to analyze some theoretical convergence, that's very, very challenging for the nonlinear cases, non-convex, non-smooth, and nonlinear. So I don't know how to do that. And not too many people know how to do that. In the literature, we do have some papers discussing about the convergence of the PD of the parameter dual in optimization in finite in Hilbert space or in the Euclidean space. But there are a lot of assumptions. I don't think they're very practical to be verified. So forget about this. And then we can say for the complicated PDE context, I don't think that we have any meaningful theoretical assertions about this. That's the PD. Okay. But anyway, so I give you actually if we use the parameter dual idea, one of the subproblems is very simple. It can be solved by a closed form solution. We have nothing to do optimization. But the other one, okay, it's not easy. So the primary workload is to compute, to do this to solve the other subproblem. But we have to compute this, and don't forget this comes from the state equation. This comes from the joint equation. So we have to solve 2 PDs as well for the subproblem. Okay, so it's properly decoupled into parametric PD subproblems for each step. Still, okay. And then our main message, as I mentioned, is the operator learning can be applied, and we don't need to do the retraining after doing this. So this is the details. I'm not sure you like this or not. It's very tedious. Let's see how do we train the model. So anyway, so you see, let me try to give you the main idea. So we assume S is the solution operator of the PDEs, but with different parameters. Okay. And then we get some data. So of course, we aim at approximating the solution, the S, the operator, with a neural network, S theta. Basically, we approximate the S by S theta, and the S theta, S can be represented as, a numerical discretization. And the neural network takes, take the discrete as U as input, and output is the S theta. So we have data set, of course, with different input functions and points and evaluations, and then we solve this very simple quadratic program, and we get the parameters, and then we get the surrogate model for this. That's the standard way. Nothing new here. Just use the operator learning ways to do that. And then so the approach is we apply the operator learning to the state equation, and train a neural network. And similarly, we train a neural network for that joint equation. We train 2 neural networks. Okay, for S, and then that's the operator. That's the algorithm. So outside is the parameter dual, nothing new. Inside is the operator learning, nothing new either. So we just embed the operator learning into the parameter dual. That's the main idea. Okay, and then we can get the algorithm. I think. Let me see it again. The non-smooth term is addressed by the proximal term G here, and the nonlinear and the non-convexity term, which comes from S, will be addressed by the operator learning method. So basically, we just slow away of the difficulties in the operator learning. That's normal. Whenever you're talking about deep learning, that's normal for doing this. Anyway, so some comments. Our approach actually can be specified as a concrete algorithms for various specific applications. That means, if you still remember the model, the genetic model, I didn't specify anything about S. I didn't specify anything about the theta. Okay, whenever you give me the S, a specific PDE, there's a specific application, and I give you a specific concrete algorithm. Okay, so it's a framework. It's not a real algorithm. It's a framework. So it's whenever you have a specified problem, I give you a specified algorithms. Okay, so we require implementing 2 forward passes of the neural networks, and some very single, algebra, operations like the multiplication of matrix and the vectors. That's it. So our new algorithm does not require solving any algebraic system. That's a very big difference from the traditional algorithms. Okay, so we don't need to solve any huge system linear equations, which is different from using the finite element, finite difference, the traditional algorithms, and we don't retrain any neural network, which is different from the current deep learning method. Okay, so no retraining is required, even for solving problems with different parameters. Okay, so that's some comments. Let me give you a very specific, concrete examples. Like we consider the sparse bilinear control of the parabolic equation. So we specify S in this equation, PDE. Okay, and then we do this, a sparse bilinear. So sparse means so we use L1 norm, and obviously we have additional, box constants. We got the admissible set, That's very standard, model to do the control for the parabolic. We just specify S as this, and we specify theta as this, nothing else. So we can just repeat what I have done, and I get the algorithm. Okay, as I mentioned, if you change to another equation, I get another algorithm. Okay, so this is the proximal operator. I can tell you, actually, we can get the closed form solution easy for one of them. For the other one, the joint equation, so we can do the training like in this way. I skip them. So it's sufficient. I just want to say it's sufficient to train a single neural network for both the state and the joint equation for this particular case. Actually, for this particular case, it's even better. Because of the special structure, we can just train one neural network at each step, not two even. In general, we need to train two, but now for this, we train one. And in particular, we apply the Fourier neural network, neural operator, okay, to approximate solution operator. We can choose different ones. I have no recipe to tell you which one should be chosen. But it depends. It really depends on the applications. But for this application, we found the Fourier, the F and O is particularly efficient. No reason. I mean, it's just because this model is very special for neural network. And then so we train. This is how we train. Okay, again, we just try to construct the loss function. Then we do this, and we tune the parameters, and we get a good one. So in general, there's no uniform guideline for choosing the best operator learning method. I don't think anybody has this, best one. It really depends on the application. So the accuracy and the performance of different operator learning methods heavily depends on the underlying PDE. Okay, you give me the PDE first. So our heuristic is to apply the deep ONet for PDE defines on low-dimensional domains and the neural operators for high-dimensional domains. I don't know why, but this is just our experience. If the PDE is low dimension, maybe you recommend a deep ONet. If otherwise, maybe you recommend FNO or some other neural operators. I don't know. So just, because to observe the lower dimension, lower computation and the memory cost of the neural operators. So we consider this. Anyway, so this is the parameter dual operator learning for the sparse bilinear parabolic control problem. That's the details of each step. How do we implement the algorithms and the tedious details. So I just give you how do we set up the problem and for the training case. So you see, we train this is how we constructed the sample functions. Okay, we used these numbers and we do the training. Very simple training. We just use the MATLAB PDE toolbox to get the solutions, and then we train this. Of course, this is artificial. Okay, I'm not a if you apply this for the real application, I have some experience with industry, and I know very well actually when you try to solve a real application problems, this is not the case. Okay, but anyway, academically speaking, we can still use this to get the synthetic data sets, and then we try to get the some idea first. So we constructed this FNO, and with 3 hidden Fourier layers, and the G-Leroux activation function. This is the details of the neural network, and then we train the state equation S by minimize the loss function, and we use the Adam as the optimizer. All these are very standard doing this, and you can see the numerical experiment. I skip all this detail, but I'm going to show you the tables for the comparison. You will be surprised to see this. So you see, we use this one, parameter dual for operator learning, or we use the SSN standard. This is classical. We use the finite element, or we use the ADM with finite element. You see this. You see the time. You see the difference of the computation time. It's not in the same level. Okay, we need less than 10 seconds. If M is, if you choose the size in 256, we need less than 10 seconds. But the ADM will need maybe 10,000. SSM maybe need 2,000, 2.5 thousand. It's unfair to say this, but because I think this is training time. We need so much training time. I'm not cheating you. Okay, so we need so much time for training first of all. But as I said, after you train this, then you gain a lot. So we spend the most of the time for training. But after you train this, I don't even care about different parameters, different even the mesh size, different size of problems. It doesn't matter. Then after you finish the training, the remaining part is just the matrix and the vectors multiplication. It's algebra multiplication. It's just very, very fast. Especially if you have GPU, it's even faster. Okay? So 2 days later, I'm going to give another talk in another university, and I'm going to talk something totally different from this. I'm going to talk how to use GPU to accelerate the computation, which is relevant to this, but not the same. You say, so the problem is, okay, we have to pay some cost for training. Now, after we finish the training, all the things are, are just ready. We need no time to get the solution, basically. And of course, you may challenge me, how can you get the the good training result? Yeah, that's not a problem. We need some better data set. We need to choose the better training way to do that. And if we have to do fine tuning, yeah, of course. So we have to know. So, this is some question. This is some problems. Actually, I want to discuss with both academia people and the industry people. How can we, as a scientist, how can we help the AI or large language model to improve their quality? So that's very, I'm going to give a talk later about how to do the fine tuning, how to do the reasoning for a large language model. Okay, but on the other hand, if you talk to some industry people, I talked to many, and they give me some very opposite suggestions. They said, okay, 90% of the LLM, the efficiency, comes from the data, the quality of the data. 70%, the importancy. 20% comes from the computing facilities, GPU, hardware. Only 10% comes from the algorithm improvement. Okay, and that's for me. It's a shock news, right? So we make a life from the algorithm. So we spend all the time for algorithm design. But even you do the best in the world, you can only save at most 10% cost for the industry. 10% only. But 70% comes from the data. So how can we help the industry to generate some better data sets? That's more important. So how can we help them to do this? We need some experts to make the data better, or to make the real world, or make data sets smaller but higher quality. We need to represent the data. We need to represent the physical world by some field data but better data. So that's something we have to do. For example, if you're expert at PDE, and you should help some people to do the training part. Instead of design the algorithm, I'm doing design the algorithm, I'm doing the 10% part. But the PDE guys, the PDE expert can do the 70% part. To try to get some better training ways, better training data sets, that seems to be more important, according to my conversation with industry people. Okay, that's not a good news for scientists, in some sense. Okay, we are doing mass storage, we are doing proof, right? They say, okay, that's not important. Forget about that. Okay, anyway, so, but still, as a scientist, we love this theory, we love the math behind this. But I'm going to tell you, training time still a lot, but after training time, nothing, almost, we can just forget about the time. So remark, so the training of the FNO is a one-time cost, and then no retraining is required. So the training cost of the FNO can be amortized if the model is solved repeatedly with different parameters. Just repeat, okay? I try to give you a conclusion in the last few minutes, so I'm going to finish it earlier. So we propose a primary dual-based operator learning approach for solving a general class of nonsense optimal control problems with nonlinear constraints. You see, this problem was unsolvable, numerically, okay? We didn't see any hope to solve this problem numerically. Can you imagine, actually, we're going to solve a optimal control problem with nonlinear PDE? Even for nonlinear PDE is very, very difficult, as I mentioned. No speaking of the control problem of a nonlinear PDE. It's very, very difficult. So we didn't have any hope to solve this numerically. Of course, people start to work on this, from different approaches, like theoretical stuff, something like this. But I didn't see any efficient, algorithms to do that. And I tell you the truth, actually, for some industry applications, we need the real-time applications. We need the real-time solutions. So we have a very high demanding of the speed. So that means we have to solve this problem very immediately. Otherwise, the solution is useless for us, for industry. So we really have to, we have to compound different expertise. Like we use the optimization primary dual idea to separate the non-smooth and smooth part. We take apart this non-smooth and smooth part, and we have to use the operator learning, to try to learn the operator in the PDE, so that, as I said, so after training we don't need to retrain any neural network. So this is really a fusion method where you have to combine very classical optimization from very contemporary machine learning algorithms to do this. So in some sense, actually, the proposed approach, we combine the efficiency and the generalization of operator learning. And on the other hand, we leverage the model-based property of the prime dual method. Okay. So our method differs from existing algorithms in some way. For example, we do not require repeatedly solving the algebraic systems after discretization, or we don't or retraining neural networks. So it achieves a very good accuracy. I have to say, accuracy is not even a problem for some applications. People always challenge, actually, if you use machine learning, for example, use pins, the accuracy is not good. Yes, for most of the cases, it is true. Okay, but for our case, for example, we use primary dual and then operator learning. Of course, depends on the how you train, as I mentioned. If you train the neural networks very good, learn the operator very well, actually the accuracy could be guaranteed. At least for our experiment, the accuracy is comparable with the traditional algorithms. Accuracy, completely comparable. Okay, and it's much more efficient, as I said, after training. So it represents a new way to solve such a difficult problem. The problem is just so challenging, as I mentioned. In the past years, we didn't see any solution numerically. We didn't. But now we have some, method. Of course, very, very clear disadvantages. We have no theoretical result for this at all. Zero. Some, a little bit, a little result comes from the primary dual optimization algorithm, but that's just the outside layer. The inside layer, the deep learning part, has nothing to explain. Okay, so still, we need to know some theoretical guarantees. So yeah, we can still extend the, as I mentioned, what I'm proposing is a very general framework to how to combine optimization and machine learning to solve some very difficult, computational mathematical problems. So we can extend, the algorithms I just mentioned to different ways. One way is actually we can, for example, we can consider the model with different PDEs and different regularizers. And for some other applications like the control constraints optimal control of stationary Burger's equation, sparse optimal control of the semi-linear parabolic equations. We have several. Okay, and you can look at the the paper. Okay, our paper. We list several. We list several such applications. So in general, our approach can also be applied. I mean, for this problem with any PDE in general, as long as the PDE has a very well-defined differentiable solution, S, because we want to learn this S. Okay, so whenever the S is well-defined and its differentiable solution is good, then technically speaking, our approach can be applied numerically. And the corresponding, of course, the corresponding adjoint equation is also numerically stable. With these conditions, our framework is applicable. And the solution operators of the state and adjoint equation can be well approximated by neural networks. So with these two conditions, the framework becomes applicable. This is the only thing we can claim. And the approximability of the solution operators may be related to their smoothness and the regularity of PDE solution. For this, we know nothing about this. We highly suspect actually the regularity of the PDE solutions this property matters for the numeric performance. So I have no idea, how to quantize the analysis and what's the rigor math behind. I don't know. But we highly suspect, according to our numeric examples and according to our experience, I think the regularity matters for the PDE. Okay, that's just some summary or some remarks on top of the numerical stuff. So we again we simply focus on numerical study, simply focus on the combination of optimization and the machine learning, and we leave a lot of theoretical works unsolved. I think this I think this is one of the first, probably the first work to combine the primary dual idea with the machine learning idea, and then we solve this optimal control problem. So theoretically speaking, we know nothing about this, and I hope you can know something, and then tell me if you know. So that's the paper, as I mentioned, you can find in the archive. So that's all. Thank you.
Thank you, Professor Yuan. Very interesting. Any questions? I have a question.
Yes.
So you saw two-dimensional PDE to generate training data, but for high dimension.
Yeah, that's the problem. Yes. Again, so then you need more data and then more time for the training. Yeah, that's the problem. I know. Yeah. You can, I mean, methodology speaking, you can use the same methodology, but the problem is time. Okay, you need more time to do that. Yeah, so I am not claiming this is better than the traditional algorithm, but I'm saying this is a new way that sometimes we can solve some problems which were totally unsolvable before. Like if you use the finite element to solve some problems, I mean the computation is, I mean, it's increased exponential. I mean, it's not easy to solve. Yeah.
I see. Thank you. Any questions?
Just a quick question. I'm curious about your comparison between the traditional method using finite element and neural networks.
Yes.
So I see. Well, it's so it seems the neural networks performance is very amazing. I say it's much faster than the traditional methods.
Yeah.
So, but I just want to know how do you. So the only difference is you use the operator learning, right?
Yes.
Use the neural network to beat the finite element solver.
Yes.
Okay, and you solve a time dependent problem, right?
Yes.
It's a time dependent. So
yes.
Okay.
The time is here. We spend time for training.
Oh yeah.
You cannot just compare this two columns.
That is unfair. Offline, right? That's offline.
Yeah,
this is
yeah.
online.
Definitely.
You don't need any retraining process.
No.
Okay.
As I mentioned, after training, it became much faster because we have no system linear equation to solve.
Okay.
Just the matrix and the vector multiplication.
And your PDE is smooth, right?
Yes.
So the PDE is smooth, but the constraint is
the regularizer term is non-smooth.
Okay. Yes. Okay. So then the neural network can approximate the operator accurately.
Yes.
Okay.
Otherwise, you cannot use the neural network because the loss function is not smooth. So the idea is that we use ADMM or primary dual to separate the regularizer non-smooth with the PDE part. So the PDE part is completely smooth. The other part is non-smooth, but it's a very simple non-smooth. So we have closed form solution. That's the idea.
Yeah.
Thank you. Any questions? If there are no other questions, let's thank Professor Yuan again.
Thank you. Thank you so much.